Now we have Raghvendra next.
Yes.
Yes.
Yeah.
Can you share?
Yes, I'm trying to.
Okay.
Can you see my screen?
Yeah, I can see. Perfect. Yeah. So Raghu, you have 12 to 13 minutes and then a couple of minutes for questions. I will tell you when your time is almost up.
Sure.
Okay. So we are really happy to have Raghvendra Singh from IMSC, who is going to tell us about covariant formulation of generalized uncertainty. Okay, go ahead, Raghu.
Yeah, thanks for inviting me. So I'm going to talk about the covariant formulation of GUP. So outline of my talk is like the following. I will first introduce the GUP and well-known GUP models. Then I will present the covariant approach that is totally based on the normal coordinates. And after that, I will discuss about the geometry of momentum space. And including the above two bullet points, we will frame our GUP formulation and then conclude. Yeah. So Heisenberg uncertainty principles tells us there should be fundamental limit for measurement accuracy with which certain pairs of physical observable like moment, position and momentum and energy and time it cannot be measured simultaneously at arbitrary accuracy. So what if one probe a high energy limit or high momentum limit? Do we need to consider the gravitational effect since such high energy affect the background space-time? Yeah, the first case is yes, of course, yes. So how do we include these effects in Heisenberg uncertainty principle? So Heisenberg principle get modified at large momentum with the Planck scale at the as the characteristic scale at which the modification occur. So we introduce people usually introduce a theta that is a function of position and momentum, and depending on the function of theta, there are a lot of well-known GUP theories. Those are given below. Yeah. So the consequence of considering theta that is a function of only momentum. In that case, there will be non-commutativity appear in the position coordinate, and if the theta is a function of position only, then there will be the non-commutativity momentum. And if theta is function of both, then there will be non-commutativity in both position and momentum. This is the consequence of a Jacobi identity. If we include the Jacobi identity, we can get these results easily. Yeah. So why we need covariant approach and what is it? So the generalization and interpretation of Heisenberg algebra in a free relativistic theory, which is also invariant under general coordinate transformation, is not straightforward, because the key issue is trivially evident from the explicit appearance of xi in the commutator relation, which is plus any of general covariance, because we know that xi is not a vector in general space-time, because xi is just a label on a chart, coordinate chart. So this is problematic, and it spoils the covariance. Therefore, in curved space-time, generalization of Heisenberg algebra requiring covariant definition, and in order to that, we define the normal coordinates. What is so these are the normal coordinates. Riemann exponential map stabilize a local parameterization of a small region around a location P0. That is a point in the manifold in terms of coordinate of the flat vector space, that P0. This is the vector space, and the exponential mapping is a mapping from the tangent space to the manifold, such that we can representing the manifold in normal coordinates. So normal coordinates can be write in this manner. So in this thing, we can see that the geodesics, so this is the geodesics, and we are writing in the normal coordinates. We can write this as the follow, and this representation, it is we can see that it is like a straight line because it has the form of like y equals to mx. where the TA is the fixed vector at the P naught. So how to vary the normal coordinate? So varying the normal coordinate will be dependent on the two things. So if we fix the geodesic length lambda and vary the vector at P naught or the reverse way. So for the first term is going to give the extrinsic curvature. Here epsilon is a shift of the P naught. So this has the component along the direction of tangent vector and orthogonal to tangent vector. But the component in the direction of tangent vector will vanish the KAB term because KAB is orthogonal to that is a normal to the hypersurface. This with KAB UB going to give you 0. So finally we will get the change in normal coordinate in the following way. So and this term is going to give you the TATV, and epsilon B is a shift that is we are going to change in the base point or some field point. So when M represents the space-time manifold, the normal coordinate becomes this. So we here phi a like x, and the variation of the normal coordinate suggests that commutation between x and the P will be this. So in the normal coordinate, the Heisenberg algebra becomes like this. Here the theta function is these things. So this appears naturally by just varying the normal coordinates, and this is this becomes the delta AB when we write it in the flat space-time. So it is going to give you the ordinary Heisenberg algebra in the flat space-time, and in the curved space-time it is going to give you this. So this is a modified theta in the curved space-time. We will now turn the case when M represents the momentum space and look for the kind of deformation that geometry of momentum space can produce in the commutator. So we need information about the equivalent geodesic surfaces and extrinsic curvature in the momentum space, and for this we need first characterize the geometry of momentum space. So we are going to construct the momentum space geometry by just taking the motivation from the Lobachevsky space that is given by that is a relative velocity space between two particles in the following way. Here the chi is a rapidity, and so we can write the relative velocity space in this fashion. So we are going to construct a geometry of momentum space. So we need to consider following 2 points. The first is that the four momentum geometry to be Lorentzian, and the second one is like four points in the momentum space have zero relative velocity. The metric gives the difference in the rest masses associated with corresponding momentum. So if we put dl square is equal to 0, then we should get dl square is equal to minus dm square. This is a relative velocity space, and this is a for length space-time length. So in momentum space, considering all points, we write the metric in the following way. So I'm going to say about what is f and mu in the next slide. So here f is a dispersion relation. So ordinary dispersion relation is equal to like p square is equal to minus of m square. Here we are including a dispersion relation that is some smooth function of p square is equal to minus of m square, and mu square is some function of m. So that we want to put generalized. We want to discuss about the generalization of the geometry of momentum space. So that's why we are putting the dispersion relation, and the mu is not equal to m. Mu is some function of mass. So if we can see that this line element is going to give you flat Minkowski metric in hyperbolic coordinate if p square is equal to minus m square. But if we put other in general dispersion relation, that f of some arbitrary function of p square, that going to give you the curve momentum space with the following curvature. So this is to show that this is not a flat anymore. In terms of dispersion relation, so now we are proposing our GUP relation, that is GUP formalism, that is totally based on the normal coordinates and its variation and the curve momentum space. So since we have shown that when we vary the normal coordinates, we get the XAPB is equals to lambda KB minus TAT with them. That going to give you this thing, this expression from this metric, using this metric. Yeah, but by the use of normal coordinate and recognize that M represents the geodesic length from the origin in the momentum space metric, the above expression then becomes in the following way. So we going to call it G1 and G2 for the further discussion, because these are a bit complicated. So the remaining commutators then follow the straightforward application of Jacobi identity, because since theta is a function of momentum only, so momentum is going to commute, but there will be non-commutativity in position, and we can see that in there is a non-commutativity in position, but for the ordinary p square is equal to m square, since in that case that is going to give you this term going to give you 1, and this is going to vanish. So in the ordinary p square is equal to m square thing, that we are getting the ordinary Heisenberg algebra.
Raghu, can you wrap up in a minute?
Yes, almost. Yeah. So what will be the dispersion? What will be the non-commutativity in position, and what will be the Heisenberg algebra, or that we are going to say that GUP? So for the dispersion relation, these are three dispersion relations we are going to plot. So we can see that a low energy limit. These two are giving the ordinary Heisenberg algebra, because this G1, if you remember, G1 is a coefficient of delta AB, and G2 was giving the quadratic momentum term. So in the low energy limit, that is going to be ordinary Heisenberg algebra, but in high energy limit, it's not. So this is like a kind of yeah. So we have presented a geometrical formalism for the generalized uncertainty principle, which is covariant and connect the feature of underlying geometry with the deformation of canonical commutation relation. When the manifold is the momentum space, we characterize its geometry in terms of four-dimensional extension of Lobachevsky K space, whose Riemann curvature is defined by the totally dispersion relation. So our work interconnect the generalized uncertainty principle, momentum space geometry, and modified dispersion relation. Yeah, thank you.
Okay, sorry. Let's thank Raghu for a very nice talk, and we have maybe 1 or 2 minutes for questions. I don't see any raised hand.
So can I ask a question?
Yeah, Shyam, go ahead.
Okay. I'm sorry I missed the initial part. I had to step away, Raghvendra. So can you make this for, can you make this for relativistic fields as well? Can you extend it to relativistic systems?
Yes. So it is like it's totally a mechanics up now. So for the relativistic field, we have not done it. Because it's working for the two-particle system only up to now.
Okay. Thank you.
Okay, Raghvendra, maybe I can ask a small question. So if you look at your commutator between X and P.
Yes.
And so there was a complicated F function.
Yes.
Can you show that? Maybe it was a previous slide.
Okay, sorry.
Yeah, this one. So I mean here X and P are operators, of course, in the commutator, and the Fp square is m square, as you said, right?
Yes, yes, minus of m square, yes.
But the p square in the denominator is some inverse function of m square. So that, I mean,
yeah,
so is there some very complicated operator in the denominator? I mean, how do I understand this thing on the right hand side?
P square is mu square. Like, so p square is equal to minus mu square, because as we are correcting the f of p square is equal to minus m square, we cannot say like p square is equal to minus m square. P square is some mu square. So mu is a function of some m.
Yeah.
So
but, I mean, is this a C number term proportional to identity operator, or is it some complicated composite operator of momentum? That's what I wanted to ask. This term that is there in the right hand side, because it's acting on some wave function, right?
So it's acting on some wave function. So the first term, this is scalar, and delta AB is going to act on. And in the second term, like, yes, so we can write the.
Okay, it's just a second order operator.
Yes, yes, yes.
Okay, thank you.
Yes.
Okay, if there are no other questions, then let's thank Raghvendra, and then.